Hi there. In the last video on the PZEM-004T module, I left you with this, showing how to use it, for example, with the software for my GitHub page. In this video, I want to talk about what accuracy you can expect from it. We start with AC volts. This diagram shows how I tested the voltage accuracy. This sounds easy. Just compare the readings from a good multimeter with what the PZEM-004T reports. The trouble is that mains voltage is far from constant. Even if you take measurements of the multimeter and the module as simultaneous as possible, each device has its own delays in acquiring a valid reading, which means the voltage can change and the two instruments show a difference that has nothing to do with the accuracy they read. The other problem is that I want to check the accuracy not just for 50 Hz AC in the UK and Europe, but also to check 60 Hz for my viewers across the pond. My solution for this is the setup here. The AC comes from my function generator, which means I can pick any frequency I want, but the maximum output of my FY6600 is limited to about 7.1 volts RMS or 20 volts peak to peak, which is way too low for this test. Its current is also too limited to drive the 3 or so ohms of the secondary side of a mains transformer directly. To fix that, the output of the function generator goes into a power amplifier, which provides sufficient power and amplitude to drive the secondary of the transformer. It turns out I only have to set the function generator amplitude to 0.8 volts peak to peak to get 250 volts RMS on the primary side. With a script on the PC incrementing the function generator output by 5 mV each step, this translates to 160 steps of about 1.5 volts on the test voltage. This voltage is measured by my Agilent 3441A and the PZEM-004T, and the data is collected by a Python script on the PC. Of course, the whole thing needs to be run twice, once for 50 Hz and once for 60 Hz. The result is this graph. You can see that the accuracy of the module is actually very good, right at the promised 0.5% over the whole range, and the difference between 50 Hz and 60 Hz is negligible. The reason why the graph goes steeply up on the left is that percentage-wise, the error of 1-digit difference becomes more severe the lower the value. This is just math of expressing the difference in percent, and I have explained it many times before. The PZEM-004T is limited to 0.1 volt resolution, which is the reason for the spikiness of the graph, and the higher the voltage, the less 0.1 volt difference matters in the calculation, which is why the jaggedness gets less and less on the right. Overall, I'm quite happy with the voltage accuracy of the PZEM-004T, which is true RMS, by the way. Of course, if you do the modification described in the first video, the accuracy of your module directly depends on how well you match the replacement R17A and R17B resistors to the original R17. But since my resistor pair matched to a difference of 100 ohms or so, the unmodified PZEM-004T should have the same 0.5 accuracy. My setup for testing current accuracy is quite similar. Again, the function generator drives an amplifier, which is now used directly to push up to 1.4 amps of current through the 10 ohm load resistor. The Agilent 3441A and the PZEM-004T both measure the current, and the PC collects the data from both and drives the function generator to do the test in 100 steps, incrementing the current through the load by 14 milliamp each step. For current, I need to run this not only first for 50 and then 60 Hz, but also repeat both tests using first the ×1 and then the ×10 switch. This is where scripting really pays off. The reason for the jaggedness of the graph, its gradual smoothing out towards the right, and the high spikes on the left are the same as before. The first observation is that ×10 mode, shown dashed, is more accurate than the ×1 mode, yet at around 1.2%, still quite a bit worse than voltage and not exactly what the spec promised. There's also a tiny difference between 50 and 60 Hz, with a 60 Hz accuracy slightly lower, possibly because the current transformer is optimized for 50 Hz. I should also point out that the chip expects to be calibrated for the specific current transformer used. It has correction registers for the current and the phase shift caused by the transformer itself. The fact That this kit comes with a choice of 2 different transformers makes me wonder which, if any, was used for calibration. The behavior of the ×1 and ×10 is not quite what I expected, and a bit of a mystery to me. You see, at the far right we have 1.4 amps in ×1 mode, and close to the left is 1.4 amps in ×10 mode. Because 440 milliamps test current in ×10 mode, the module actually reports 1.4 amps, and the 1.4 amps on the right are reported as 14 amps. For this graph, I corrected the ×10 readings, of course, by dividing the reported values by 10. I expected the current transformer to be less accurate at very low currents, like this test that uses only 1.4 amps max. After all, it is rated for up to 100 amps, but I expected the ×1 accuracy to improve with higher currents at the right. More importantly, the accuracy value at 1.4 amps to match the value of 140 milliamps for ×10 mode, but that is clearly not the case. The ×10 mode accuracy is consistently around 0.3% better, and I'm not sure why. If you have any explanations, please leave them in the comments. In the hope that different accuracies for the 2 modes would eventually merge and disappear at higher loads, I tested the module using a 2 kW fan heater. This uses of course AC mains directly and is therefore limited to 50 Hz. With just 2 samples, it's hard to speak of a trend, but it does look as if the measurements become more accurate the higher the current. But the difference between ×1 and ×10 accuracy stays the same. In ×10 mode, the 8 amps is actually measured as 80 amps, so we are covering almost the complete range of a 100 amps current transformer. In any case, it appears that adding the ×10 mode is definitely a good idea, but I would like to caution that you should avoid switching between ×1 and ×10 under load, as this generates a huge spike, which is sometimes enough to disrupt the communication on the serial interface. On to frequency, and for this I essentially reused the setup for verifying the current accuracy. It is interesting to note that the module measures frequency far beyond the specification. Measurements start at 25 Hz and I stopped at 1 kHz. It is clear, however, that the module is optimized for the 45 to 65 Hz range, and in that range the accuracy is very good, between 0.1 and 0.2%, the higher error mainly because of the 0.1 resolution limit of the module. Beyond that, frequency errors get more and more erratic, but stay within roughly 1%. Current and particular voltage accuracy are declining quickly at 100 Hz and beyond. Last in line is perhaps the most vexing quantity, power factor, and all these different values, apparent power, active power, reactive power, and so on. My first attempt was to compare the PZEM-004T with this AC panel meter that I modified to read from 0 volts, which is now part of my Variac. This one uses a completely different metering chip, so if both report similar values, it is more reliable than comparing it with my other power meter that uses a chip from the same Wango V98XX family as the PZEM-004T. The problem with this approach is to find test objects that have different power factors and that draw a decent amount of current. The latter is needed because this panel meter does not have a ×10 mode, so it needs sufficient current to read correctly. This means more than what an LED light bulb usually draws. In the end, I used a switch mode power supply, allowing me to vary the DC load, hopefully resulting in different power factors. Here it is loaded with providing 3.3 watts DC into the power resistor. The module in the Variac shows 8.2 watts compared to the PZEM-004T's 9 watt. The apparent power is 14.2 volt ampere compared to 17 volt ampere. And the power factor is 0.57 compared to 0.53. The current of 60 milliamps is probably still too low for better accuracy. Cranking up the power supply voltage increases the DC load to around 13 watts, resulting in 19.1 watts active power on the Variac compared to 20.5 watts on the PZEM-004T. Apparent power has risen to almost 30 volt ampere versus 33.3 volt ampere on the PZEM-004T. And the power factor reads 0.636 versus 0.6. Increasing the DC load further to more than 31 watts and the active power value now reads 38.9 watts on the Variac and 40 watts on the PZEM-004T. The apparent power values are 58.2 volt ampere and 62.3 volt ampere. And the power factors now read 0.667 and 0.64. I plotted the results of the 3 tests here and added 2 more tests, number 4 using an idle AC transformer as load and number 5 loading that AC transformer with a power resistor on the secondary. This graph shows actual values and not the usual error graph because I can't tell which of the 2 modules is better and could act as a reference. All I'm looking for here is that the blue traces for active power, red traces for apparent power and green traces for power factor are reasonably close. It's a rather limited sample set and fraught with the already mentioned problem of AC mains voltage fluctuations during the test, but I think both modules are reporting reasonably similar data. Nevertheless, as a verification of power factor accuracy, this method is not very satisfying. There is an alternative, which is to use the phase shift between a sinusoidal voltage and current waveform. In this example, the light blue current trace is ahead of the yellow voltage trace. It crosses 0 here, and sometime later the voltage also crosses the 0 line. The time difference is called delta t and can be measured. Using the fact that a full period is equivalent to 360 degrees, it is easy to calculate the phase angle phi that corresponds to delta t. The 50 here stands for 50 Hz frequency. Just replace that with 60 if your mains frequency happen to be 60 Hz. Once we have phi, we can calculate the power factor as its cosine. Because the light blue trace is ahead of the yellow voltage trace, it is called a leading power factor and indicates that the waveform is caused by predominantly capacitive loads. Inductive loads cause the current to lag behind the voltage. While this is the historic definition of power factor, pure sine waves are a rarity these days, so this situation does not happen very often. Still, the measurement circuit must be able to deal with it as well with all kinds of distorted waveforms. The easiest way for me to force voltage and current with a defined phase shift is to use the 2 channels of my function generator and synchronize them for frequency and waveform only. Then I can simply dial in a non-zero phase offset between channel 2 and channel 1. It is necessary to temporarily modify the PZEM-004T wiring in its enclosure to allow to feed voltage separately from the current path. It is very important to get the probes connected correctly. Both function generator outputs have a common ground and the same is true for the scope inputs. It is therefore essential that the ground leads of the scope inputs are connected to the same common ground of the function generator outputs. If you would reverse one of the scope probes, for example channel 2, you would short channel 2 of the function generator. If these were reversed, its output would be connected to scope ground through the blue probe and its ground to the same scope ground via the ground lead of the yellow probe, and since all the scope grounds are connected to each other, the function generator channel 2 sees a short circuit. While using only function generator voltages and current for this test is good for safety, the values are borderline of what the PZEM-004T needs to get accurate measurements. The modification to allow voltage and current to be provided separately is easy. Just remove this wire from the terminal and add a temporary wire to allow direct connection to the function generator channel 1 output. Since the whole test uses only harmless voltages and currents from the function generator, all that flying wiring is okay in this case. The power resistors are definitely oversized for this test, but I love using them because they are very convenient. The scope shows the traces of the light blue current and yellow voltage. The phase angle is currently at 0. If I change the phase angle between the 2 channels on the function generator to 50 degrees, you can see how the scope picture changes. At the same time, the phi readout changes in the PZEM-004T. Note that the last row shows values that my software calculates out of the ones measured by the module. One of the values shown is the phase angle phi calculated from the power factor 0.59. Phi is with 53.8 degrees slightly high, as the function generator was set to 50 degrees. But how do we know that we can trust the function generator? We can use the scope's cursor function to measure delta t and calculate phi. In this example, I enlarge the area of interest by changing the time base to 1 millisecond. To calculate phi, all we need is the readout bx minus ax as delta t, which is 2.78 milliseconds. Plugging this into the formula shown earlier yields an angle of 50.04, which correlates well with the function generator value of 50.0 degrees. This is equivalent to a power factor of 0.64, while the module showed slightly less at 0.59. To see if more current would make a difference, I did add the power amplifier back into the setup, but the results were essentially the same. The shown power factor in green here is always a little lower than the expected value, which is the purple curve. At least the increased current allows me to check ×1 mode, and the values were so close to ×10 that they mostly plotted on top of each other. So what to make of power factor accuracy? One would expect that measuring a phase angle difference could be done a lot more accurately, but as I mentioned before, this kind of situation is very unusual, as in real life mains voltage and current curves are never very sinusoidal and often extremely chopped up and distorted. In fact, because of that, the chip in the PZEM-004T doesn't even look at the phase angle and instead uses a completely different way to calculate power factor, namely by using the ratio between apparent and active power. This works even for heavily distorted waveforms, but it's more complex than what fits into this video. The key point is that it first needs to calculate power, which means it needs an accurate current, and as I have shown, the current measurement isn't better than 1.5%, and the lower the power factor, the less active power is remaining for that calculation, which explains why the trace is close to the theoretical value at high power factors and deviates more at lower power factor values. For now, let's just say its reported power factor in this test is certainly within the ballpark and usable, even if the promised 1% are not reached. I would expect that with more current the power factor accuracy will improve, simply because the better signal to noise ratio and the math has larger values to work with. And speaking of values, here's a little tool I developed to read data from the PZEM-004T. You can download it from my GitHub page, link in the description. You need to give it a port to which the module is connected, of course. The first two rows are all data the PZEM-004T produces, polled every 0.5 seconds. The last row shows some useful values calculated out of these. This GUI 10 6-watt light bulb with a power factor of 0.5 draws a real power of 5.5 watts, its equivalent phase angle is 60 degrees, apparent power is 11 watts, and its reactive power 9.5 watts. If I switch my box to ×10, you can see that the current and power becomes 10 times larger. To compensate, you can click the ×1 button and switch the display and recording to ×10 mode as well. You see, this gives you one extra digit position on the values, which is why this feature is so useful. Clicking Rec turns on recording using a unique file name based on a timestamp ending in .csv, because it's a comma-separate value format. By default, the recording time interval is every second, and the number shown in front of the file name shows you how many records have been written so far. You can change the recording interval at any time using the selection on the right. The values are sampled every 0.5 seconds. If the recording interval is greater, the default mode is that the program records the average value. So at 1 second it averages 2 samples, at 2 seconds 4, and so on. Switching back to ×1 mode for a moment, because I want to show that the selected mode is included in the recording. Turning Rec off closes the file and turns recording off. Clicking Rec again creates a new recording file, for example using a slower interval. You can see that the number of records written is now increasing much slower. I have changed the load to a 60 watt incandescent light bulb with a power factor of 1. The real power matches the apparent power and the reactive power is of course 0. Again, times 10 mode gives a better precision. Let's have a quick look at the recording format. CSV should be usable by any spreadsheet program. I'm using LibreOffice here. It takes a bit to load as this laptop is relatively slow, more than 10 years old. On the top you see the field names which match what was shown on the screen. X mode field shows whether you pressed that times 1 or times 10 mode button. Now to be clear, the software has no idea of the actual switch setting on the box, so the consistency of this depends entirely on you. One last thing, the energy value is accumulated and saved internally in the PZEM-004T. As sort of a hidden feature, if you press connect again, if you are already connected, this action does nothing except resetting the energy value to 0. Just to prove the point, this is the same program running under Windows 7. I don't have a Windows 10 machine with Python 3.8 or better available at the moment. Apologies for the slightly blurry picture. This program behaves exactly the same way as the Linux version you just saw, including times 1 or times 10 mode or recording. Finally, as you can see, you can pre-populate the port name in a command line argument, but you still need to press connect to actually do the connection. The other flag allows you to suppress the averaging between entries if the recording interval is greater than 0.5 seconds. In that case, the recording simply ignores any values that fall in between the time interval. What can you do with the PZEM-004T apart from energy usage monitoring? Here's an example where I used it to record the behavior of 2 solder stations set to 300 degrees Celsius starting from cold. It is quite interesting to see that the Hakko has more power and obviously more advanced electronics too, as it gradually lowers the active power when approaching the target temperature, and once it's reached, only small pulses of active power are needed to maintain it. The other one goes flat out full power right to the point where the target temperature is reached and then uses quite large pulses to maintain it. In this case, the PZEM-004T provides a lot of information about the inner workings of the connected devices without having to open them. Well, I hope you found that interesting. Don't forget that the build instructions and the software are available on my GitHub page, link in the description, and there you will also find a link to my Patreon page. Thanks for watching.